Welcome to lecture 3, where we will explore a fascinating topic in theoretical computer science and combinatorics, automatic works. This concept is a crucial part of symbolic dynamics, and we will delve into the specific example and the key theorems. First of all, two more automation. This sequence is one of the earliest and most famous example of an automatic work. It is generated by a simple iterative rule, but displays highly non-trivial properties. We will examine how an automation can be used to generate this sequence and analyze its properties. Then, the paper folding word, another interrogating sequence that emerges from physical folding process, and we will see how this sequence can be also be described by an automation and its geometric and combinatorial significance. And Cobham's theorem, a central result in the theory of automatic sequences. Cobham's theorem provides a classification of sequences that are k-automatic. We will unpack the details of this theorem and understand its implications in multiple bases. About k-automatic words, these are words generated by finite automata that read input in base k. We'll generalize the concept from the two more sequences to k-automatic words and study their key characteristics and applications. What about decidability and enumeration? Finally, we will touch on important questions of decidability related to automatic sequences, such as whether certain properties of these words can be algorithmically determined and methods for their enumeration. So by the end of this lecture, you will have a solid understanding of automatic words, their properties, and their significance in both mathematics and computer science. Let's get started. Now let's review the two Morse word as well-known sequence in combinatorics on words that avoids repetition of any block of symbols. It's generated by repeatedly applying a simple substitution rule, denoted here by the function mu. Substitution rule of mu, the two Morse sequence is generated by applying the following substitution rules. 0 maps to 0, 1, and 1 maps to 1 and 0. It's better I say that we substitute 0 by 0, 1, and we substitute 1 by 1, 0. So starting from 0, we apply mu repeatedly to generate the sequence. The first iteration gives us 0, 1. As you can see in the picture. So applying it again to both 0 and 1, we get 0, 1, 1, 0. Okay. Continuing this process indefinitely, we generate the infinite sequence. Expression of the two Morse sequence can represent the two Morse word by t as t, which is equal to mu of t, and you can get t of 0, t of 1, and so on, so on. This results in the infinite binary sequence. You can see we have a two Morse sequence. Notice the absence of consecutive identical blocks, which is a key property of this sequence. Recursive definition, another important feature of the two Morse sequence is recursive structure. You can see that t of 2n, which is equal to tn, and t of 2n plus 1, which is equal to t bar Tn, where T bar is the complement of Tn. So every odd index is a complement of the corresponding even index. So because we are working with binary alphabet, that's why it makes sense. This recursive property is crucial when we study its automatic nature, and it reveals a deeper self-similar structure. This also connects to how finite automata can be used to generate such sequences efficiently. In the next part of the lecture, we will look into the automation that generates this sequence and analyze its properties with detail. Okay, so to deepen our understanding of the two-Morse word, let's explore another description of its construction, which highlights its recursive nature and the binary representation of indices. Recursive structure, as we saw earlier, the two-Morse word can be defined recursively by t of 2n, which is equal to 2t of n, and t of 2n plus 1, it would be complement of tn. This emphasizes how the value at even indices is the same as the value at the corresponding half index, and the value at odd indices is its complement. What about binary representation? Another way to describe the indices in the two-Morse sequence is the using the binary representation of integers. Let n be represented in the binary as xk blah 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 x1 x2, which means n, which is equal to 2 to the power k times xk plus blah 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 to power 1 x1 plus 2 to the power 0 x0. From this we can derive 2n is simply the binary representation of n with a 0 appended at the end of x k till x0 in the base 2 concat with 0. Similarly, 2n plus 1 is xk till x0 in the base 2, you concat with the 1 in the right hand side. This description provides a more computational perspective on how the sequence is generated based on the position of the binary digits. It is particularly useful when implementing the two-Morse sequence algorithmically, as it highlights the relationship between binary representation and the sequence's values. This binary interpretation connects the sequence to automata theory and demonstrates how automata can be designed to generate such sequence based on simple rules applied to binary numbers. Well, now let's examine how the two-Morse sequence can be generated using an automation, a simple computational model. This method allows us to see the sequence's structure and construction from an automata theory perspective. Recursive description we have seen before. The sequence's recursive nature can be described using automata like rules. T of x2, T of x in the base 2, you can get from right hand side by 0, which is equal to t of x in base 2. Also, we have t of x2 if you can get from right hand side by 1, which is equal to t of x2, which is equal to x in the base 2, and which is equal to t of x in the base 2 plus 1 in mode 2. Actually, we need to only work with 0 and 1 because you are working in the binary alphabet. This means that if you append a 0 to the binary representation of x, the value remains the same as of for x. If you appended a 1 the value becomes the complement of t of x2 plus 1 mod 2. We have one definition of Tn. The value of Tn depends on the number of the ones in the binary expansion of n, especially T of n which is equal to 0, if the number of the one in the n in the base 2 is even, and it would be equal to 1 if the number of the ones in the binary representation of n, it would be odd. This rule captures the alternation between 0 and 1 in the two-more sequence based on the parity of ones in the binary representation of the index n. About automation diagram, on the right side of the slide, we see a finite automation representing the generation of the two-more sequence. It has two-state Q0 outputting 0 and Q1 outputting 1. When reading a binary digit, the automation translation between states based on the value. If the current state is Q0, reading a 0 keeps it in Q0, and reading 1 moves it to Q1. Similarly, if the current state is Q1, reading a 0 moves back to Q0, and reading a 1 keeps it in Q1. This automation efficiently tracks the parity of the number of ones in the binary representation of the index, thus generating the two-more sequence efficiently. In the summary, this automation provides an elegant way to visualize and compute the two-more sequence connecting the recursive and binary representation we have discussed earlier. Okay, interesting. The paper folding board. Now we want to explore the paper folding board, another fascinating sequence generated by a process related to paper folding and also describable using automata. Definition. A paper folding word W is an infinite sequence that belongs to 1 and minus 1. It would be infinite word based on this alphabet, where each element is either 1 or minus 1. It is denoted by W, which is equal to W of 1, W of 2, and blah, 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 blah. So, folding pattern, the key folding process is represented by pattern P, which is equal to 1 diamond minus 1 diamond. Here the symbol diamond indicates a placeholder for subsequent step in the folding. As the folding process continues, the pattern grows recursively and creating an intricate sequence of folds. A structure of the sequence. The value of W are determined by successive iteration of the folding process. The table of the slide shows the first few values. Okay, the value of 0, you can see always we have a diamond. And then you can see that in its stuff, you substitute instead of this structure. Again, you substitute this structure, and again, whenever you have a diamond, you repeat this structure. So this process generates alternating ones and minus ones, with the diamonds representing place where the more folds will occur as the pattern develops. Final sequence, at the bottom, we see the paper folding wall converging to a periodic-like sequence of alternating ones and minus ones. You can see here. You see we have free red, 1 blue, free red, 1 blue, free red, and so on. So This sequence has a rich structure that emerges from the recursive folding process. The paper folding words has interesting applications in combinatorics on words, symbolic dynamics, and theoretical computer science due to its highly regular yet non-trivial structure, actually. So right now it's my interesting picture. So let's turn our attention to the dragon curve, a striking example of a fractal curve that has interesting for mathematician, artists, and computer scientists alike. But what is the dragon curve? The dragon curve is a self-similar fractal, which means that as we zoom in on any part of the curve, we see that the same pattern repeating infinitely. It is generated by a simple recursive process involving turning left and right at the specified intervals. Despite the simplicity of the process, it results in a complex and beautiful structure. What about construction? A dragon curve can be constructed by folding a strip of paper in half repeatedly and then unfolding it at right angles. With each fold, the curve becomes more intricate, and after enough iterations, the full fractal pattern emerges. But what about fractal properties? As a fractal, the dragon curve has a fractal dimension, meaning it lies in somewhere between a one-dimensional line and two-dimensional surface. This property is what gives it is infinite detail, with the same structure repeating at every scale. And what about applications of that? The dragon curve has been studied in the mathematics for intriguing properties, but it also appears in practical applications. It is related to space-filling curves and has been used in computer graphics, tiling problems, and even in physical model of DNA folding. The image here shows the ring of the dragon curve, highlighting its recursive and self-similar nature. Each segment of the curve reflects the entire structure, creating a mesmerizing and infinitely complex design. Okay, now let's talk about paper folding more over 4 later. Okay, extend this concept of the paper folding word to operate over 4 different symbols, using both positive and negative values, and introduce a substitution system to describe it. The sequence W, the sequence starts as 1, 1, minus 1, 1, 1, minus 1, 1, 1, minus 1, blah, 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 blah. This sequence alternates between ones and minus ones, and the alternating pattern is mentioned across even and odd positions. The expanded alphabet helps us visualize the structural complexity of the word. Assignment to 4 letters. A represents 1 at an even position. B represents 1 at an odd position. C represents minus 1 at an even position. D represents minus 1 at an odd position. These destinations allow us to categorize the sequence based on both the value 1 or minus 1 and the position, even or odd. But what about more substitution? Substitution rule 5, the evolution of the sequence is governed by the substitution systems like here. 5, A substitute by AB, B substitute by CB, C substitute by AD, and D substitute by CD. This rule describes how a symbol is replaced by combination of two symbols as the sequence is recursively expanded. For example, an A is replaced by AB, B is replaced by CB, and so on. This recursive substitution helps generate the paper folding sequence over time. Actually, expression of W, this sequence W can be represented as W of phi of omega iteration, I mean infinity times iteration of A, where psi actually it would be is the mapping from the symbol A, B to A1 and C, D to minus. This highlights the structure of the paper folding board as a result of infinite iterations of the substitution process, ultimately generating the alternating pattern of ones and minuses. This recursive process and the introduction of four symbols provide a richer structure to the paper folding, allowing us to study its behavior and properties more closely. Okay, let's talk a bit about Cobham theorem. We'll discuss an important result in the field of automatic sequences known as Cobham's theorem, which was proved by Alan Cobham in 1972. This theorem plays a central role in the characterization of K-automatic sequences. Cobham theorem, the theorem states that an infinite word W is K-automatic if and only if W can represent it as psi of omega of W of A for some starting letter A, where phi is a K-uniform morphism, which means that the morphism replacing each letter in the word by a block of length K. I mean, if you substitute a letter exactly for all letter, it would be same structure. For example, here it would be two uniform because A substitute by two letter, B substitute by two letter, C substitute by two letter, and D substitute by two letter. So psi is a coding, a function that maps the morphism generated word into a fixed alphabet, providing to final output sequence. And K-automatic words, a K-automatic word is one of the that can be generated by a finite automation when reading the input in base K. Cobham's theorem provides a full categorization of these words, showing that they can be described throughout uniform morphisms and codings. Significance, Cobham theorems is highly significant because it gives a formal and clear-cut criterion for when a sequence is automatic in a given base. It helps distinguish automatic sequence from more general sequences and provides a framework for constructing them. In essence, Cobham's theorem formalizes the relationship between automata, morphisms, and coding, providing a powerful tool for studying automatic sequences across different bases. The image on the left is portrait of Alan Cobham, who contributed greatly to the field of automata theory and computational complexity. Okay, let's talk about K automatic words. Okay, and explore the concept of the k-automatic words, which realize the notion of the automatic sequence by introducing base k greater than 1. So the k array alphabet, we begin with an alphabet like AK is 0 till k minus 1. This is the set of digits used to represent number in the base k. Actually, for example, when k which is equal to 2, the alphabet is 0 and 1, and for k is free, it would be 0, 1, 2. So the k automatic word definition, an infinite word like u, can get u of 0, u of 1, and blah, 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 or an alphabet is said to be k automatic. And there is said to be k automatic if there exists a deterministic finite automation with output DFA, and described as follow, denoted by purple, where Q is a set of the state, AK is the k array input alphabet, and delta, a small delta is the translation function, Q0 is the initial state, and delta is output alphabet, and lambda is the output of function. And the automata must satisfy the condition, u of n, which is equal to lambda of this value. So for all non-negative 0, where a is actually finite words. Okay, and this means the automation takes the base k representation of the number n as an input and produces the corresponding value un as output. The automation input and output, the automation A receives the k array representation of n as input and the output of corresponding element un of the infinite one. The process of the moving throughout the state and applying the output function allows us to generate the word based on the base k representation of index. So in the summary, k automatic words are generated by automata that take the base k representation of the number and output a sequence, making them highly structured and predictable based on their input base. Okay, well, as we have explored automatic sequences, it's essential to understand some important clarifications and variations of the definitions and that ensure consistency across different contexts. No problem with leading zeros, actually. So one of the properties of automatic sequences is that the leading zeros in the k-array representation of a number do not cause any issues. This means the automation will behave the same way whether or not the input number that actually has leading zeros. Symmetric is in reading directions. Definition of a k-automatic word remains consistent regardless of whether the k-array representation is read from left to right or from right to left. This symmetric ensures that the reader in which the digits are processed does not affect the final output sequence. And what about regularity of language? A word, U, or an alphabet is k-automatic if and only if for all letter A, the set of indices where U, N is equal to A forms a regular language. F of A, which is equal to N base K, and U of N, which is equal to A. So this means the positions in the K-array representation where a certain symbol A appears are structured in such a way that they can be recognized by a finite automation, ensuring that the overall board is highly regular and predictable. Stability under finite changes. Another important property of k-automatic sequences is that if you started with a k-automatic word and change only a finite number of its symbols, the resulting word is still k-automatic. This robustness makes automatic sequences stable under mirror modifications, which is a useful feature in the various applications. So in conclusion, these versions of definitions reinforce the robustness and flexibility of k-automatic sequences, ensuring that the concept is applicable in diverse settings without losing its essential properties. Okay, now let's discuss the concept of the periodicity in infinite words, particularly focusing on ultimately periodic sequences and their relationship with automatic sequence. Definition of ultimate periodicity. Okay, an infinite word W is said to be ultimately T-periodic if it can be expressed in the form U, W, which is equal to concat of U, and infinitely many times you put in the word V with length of T from the right-hand side to W, to V, to U, sorry, where U is a finite prefix, V is a block of the length T, and W omega represents the infinite repetition of the block W, as I told you. Essentially, after a finite initial segment U, the word W repeats certain block V indefinitely. So, example, consider the word W, which is equal to A, B, B, C, 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 A, B, A, C, A, B, A, C, A, B, A, C. As you can see that you cut from here, and I mean, this structure doesn't have a repetition, this structure is repeat. So we can say that it would be the length of A, B, A, C, it would be 4, it would be ultimately 4 periodic. So here U is a B, B, C, C, C is the initial finite segment, and W and V it would be A, B, A, C. Repeating block, making the sequence ultimately periodic with the period length 4. So we have one lemma. A key result is that an ultimately T-periodic word is K-automatic for every K. This lemma shows that if a sequence is ultimately periodic, it can be generated by a K-automatic process for any base K. The regularity of periodic repetition fits well with the structured behavior of automata, which makes them ideal for representing such sequences. In summary, periodicity is closely tied to automata theory, and ultimately periodic sequences are guaranteed to be K-automatic, reinforcing the connection between repetition and the regularity that the automata capture. Okay, so another Cobham. Now let's discuss a second important result by Alan Cobham from 1969, so which related automatic sequences in different bases to periodicity. Multiplicative dependent integers, I mean two integers, k and l, are called multiplicatively dependent if there exists integer r and s such that k to the power r, which is equal to l to the power s. This relationship means that one base can be expressed as a power of r, and they are closely tied to each other multiplicatively. Cobham theorem. This theorem focuses on cases where k and n are multiplicatively independent, meaning No such relationship exists between in two bases. The theorem states if K and L are multiplicatively independent integers, then any finite word which is both K automatic and L automatic must be ultimately periodic. So in other words, if a word can be generated by a finite automata in two different bases that are multiplicatively independent, the word must eventually settle into a repeating pattern. This result is significant because it limits the complexity of the words that can be automatic in two different independent bases. The only possible sequence that can satisfy this condition are those that are ultimately periodic. I think it would be a very nice result. K-kernel. Let's now introduce the concept of a K-kernel, which is fundamental to understanding K-automatic sequence. A K-kernel provides a powerful way to describe the regularity and structures of an infinite. What about definition of K-kernel? The K-kernel of an infinite word like W, W0, concat W1, and blah, 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 is a set of infinite words that are derived from W by selecting elements at regularity spaced intervals, determined by graph K. More formally, for integers I and M, we define like this. You see, we selected each space and a spatial pattern, where I ranges from 0 to k to the power n minus 1, and m is the level of spacing. It means powers of k. Each wm I represents to a new infinite word formed by sampling every k to the power mth terms starting at the position I. We have a good and interesting theorem. A word is a k-automatic if and only if its k-kernel is finite. This means that for a k-automatic word, even tau, the word itself may be infinite. The number of distinct words that can be formed throughout this processing of sampling at regular interval is finite. This finiteness of the k-kernel is a direct indicator of a structure repetitive nature of k-automatic words, making this concept a powerful tool in the classification of and a study of such sequences. In the summary, the k-kernel provides a method for identifying the internal regularities of an infinite word, and the key result is that the finiteness of k-kernel guarantees that a word is k-automatic. Okay, so frequencies of letters. Now let's focus on the key property of k-automatic words, the frequencies. The frequency of their letters and factors. This property is crucial for understanding the structure of automatic sequences and also serves as a tool for proving whether the word is automatic or not. Frequency of factors. The frequency of every factor in a k-automatic word, if it exists, is always rational. This means that if you compute how often a particular factor or letter appears in the word, the resulting ratio will be rational number. Tool for proving non-automaticity. The fact that k-automatic words have rational frequencies is not just a property of automatic sequences, but also a powerful tool for proving that an infinite word is not automatic. If you can show that the frequency of a factor in an infinite word is irrational, then you have proven that the word cannot be K-automatic. The criterion can help rule out automaticity in more complex sequences. In conclusion, the rationality of frequencies in K-automatic words provides both an insight in their structure and a method for distinguishing between automatic and non-automatic sequences. So interesting tools. Okay, is a word automatic? You want to answer to some interesting questions. Finally, let's address an important question, the study of sequences. How can we prove that a word is K-automatic? We have a one interesting question, as I said to you. How can we determine if a word is a K? This is a crucial question when we're working with sequences that exhibit regular pattern but might not immediately appear as automatic. The answer is straightforward. Build an automation, or in some cases, use morphism to prove that a word is K-automatic. Can construct a finite automation that reads the K-array representation of the index and outputs the corresponding value in the sequence. Alternatively, using morphisms and coding as described in the Cobham's theorem is another way to demonstrate automaticity. Building an automation allows us to explicitly show how the sequence can be generated in a structured manner, confirming that the word is indeed automatic. Mhm. We have another interesting question. Actually, we have previously discussed how to prove that a word is K-automatic. Now let's turn the question around. How can we prove that a word is not K-automatic? Interesting question, actually. So, how can we prove that a word is not K-automatic? We want to answer to this question. The answer is there are several strategies for proving that a word is not K-automatic. Reduce to non-regular languages. One common approach is to reduce to word to a non-regular language. This involves using tools such as pumping lemma, which shows a certain property required for regular languages, and thus automatic words do not hold for the given sequence. Find a non-periodic sequence. Another interesting way, identifying a non-periodic sequence within the word can also help demonstrate that the word is not K-automatic. Periodicity is a key feature of automatic sequences. And if a word exhibits regular, non-repeating patterns, this suggests non-automaticity. We can also find a symbol of rational frequency. As mentioned earlier, the frequency of letter in a K-automatic word is always rational. If you can show that a particular letter or factor in the word appears with irrational frequency, this immediately proves that the word is not K-automatic. Okay, sometimes it's not clear. Finally, in some cases, it can be challenging to determine whether a word is K-automatic, a word is not, K-automatic, and more advanced method or deep analysis may be recurrent. Sometimes the structure of the word can be complex enough that not simple proof applies. So in the summary, proving that a word is not a K-automatic typically involves showing that it violates one or more key properties of automatic sequences, such as regularity or rational frequencies. Okay, now I want to a bit talk about decidability and enumeration. In this final section, we focus on the decidability of properties of K-automatic sequences and the concept of enumeration related to these sequences. Actually, you want to a bit talk about numeration system. It's a part of the on subfield of combinatorics. Yeah, one nice theorem. It's founded by Emile Charrier and Nara Ramprasad and Jeff Shalit in 2011. This theorem gives a powerful result regarding the decidability of properties in K-automatic sequence. If we can express a property of K-automatic sequence W using quantifiers, logical operations, integer variables, the operation of addition, subtraction, indexing into W, and compression of integer or element of W, then this property is decided. So, in the other words, if we can describe a property of K-automatic sequence in terms of these basic logical and arithmetic operations, there exists an algorithm that can decide where this property holds. This is an important result because it guarantees that many properties of automatic sequences are not only well-defined, but also computationality very favor. I mean, it would be working. About K-regular sequences, the second theorem founded by same people in the same paper states that many sequences related to K-automatic words are also K-regular. K-regular sequences generalize the concept of the K-automatic sequences by allowing for more complex transformations, while still retaining a regular structure. This means that K-automatic sequences are part of the broader family of structured sequences with similarly useful properties. These results are significant because they show that not only can we guarantee K-automatic sequences, but we can also decide many of their properties using algorithmic methods. Additionally, the notion of K-regularities provides a framework for studying related sequences that share similar regular patterns. So let's see one example. So the further illustrate the concept of decidability in K-automatic sequences. Let's look at a few concentrated examples of properties that can be decided for these sequences. So the number of the factors of length n given a K-automatic sequence, we can compute how many distinct factors of length n exist in this sequence. The number of palindromes of a given length. Another decidable property is how many palindromes, words that read the same forward and back of a specified length occur in the sequence. So indices where palindromes start. We can also determine the exact positions in the sequence where these palindromes begin, providing further insight into the structure of the sequence. These examples demonstrate the types of properties that are decidable for K-automatic sequences and show how we can analyze their structure in detail. So I think today is enough and we understand and know some important theorems and concepts related to automatic sequence. Thank you all for your attention and engagement today. I hope this lecture has helped deepen your understanding of automatic words and the concept we have to cover, like K-automatic sequences, co theorems, and decidability. As always, feel free to reach out if you have any questions or need clarification on any of the topics we discussed. Keep exploring these fascinating areas of theoretical computer science and combinatorics. And I look forward to seeing your progress in the next season. Goodbye and see you next time.